Okay, hi, lovely Elm community. My name is Matthias Rella. I come from Austria, nearby Vienna, where I live with my wife and almost 3 kids. And I run a company called Pi Systems, in the person of myself, developing web applications. And I'm using Elm whenever it is possible. And what I love about Elm is that it is, for its clarity and its elegance, and how it guides me towards well-structured code, towards a well-structured architecture, and even a well-structured UI and user experience. And my today's talk is about ElmSEQ, a conflict-free replicated data type for text. And our protagonists for today are Alice on the left side and Bob on the right side. First, they will show us what kind of problems they encounter when doing distributed collaborative text editing. Then I will propose a solution based on a CRDT. I will describe in detail what a CRDT is. I will describe the implementation of ElmSEQ. And finally, there will be a demo. So have your laptops ready and your internet set up. We will see how this works out. It's hopefully going to be a massively collaborative text editing experience. But yeah, I cannot promise anything. Okay. So what's the problem? Imagine Alice and Bob have just found out how great Elm is, and now they want to write a blog post or something together about Elm. So Alice starts with a text document and writes the word Elm into it, and then she sends it to Bob through email, and Bob gets a replica of this document, and now they can both work on it. So they're making concurrent changes. Alice writes Elm rocks, and Bob adds rules. And then they're again exchanging emails, and they end up with 2 versions which are in conflict to each other. So Alice now grabs the phone and calls Bob and says, "Hey, Bob, we're having a conflict here. Would you be so kind and solve that?" And Bob, of course, he's a gentleman, and he does that. He does this boring job of merging these 2 documents. He decides rocks is less offensive than rules, so he decides on that. And while he's doing this boring work, Alice has to wait for the new document because she knows she cannot make any further changes on the old versions because those would be overruled by whatever Bob will be sending. Okay, so they see this problem. So they switch over to another system, Git, in a distributed way. Again, Alice creates a text document, commits it, pushes the commit to Bob. Bob has this replica. Then they're making concurrent commits. Again, Alice with rocks, Bob with rules. Then they're exchanging those commits again. And again, they're running into a merge conflict. You know that thing. And again, someone has to do the boring job of resolving this merge conflict. It's Bob again. And Alice again has to wait until this merge conflict is solved and has to wait for the merge commit before she can continue her work. So it's also not an ideal situation. So we always have this problem of someone is being blocked and cannot continue the work. So they're trying a third setup in a centralized editing service like Google Docs or Etherpad. And here again, Alice creates the text document with Elm, and Bob edits it immediately, adds rules to it, and everything seems to be fine until the service is out of order, or the internet connection is lost, or whatever, and again they are blocked. They cannot access the document anymore until the service gets online again. So what would be the ideal setup? How could we expect a collaborative distributed editing to work at best? And that's how CRDTs would solve it. Again, the same story. Alice creates a text document, Elm sends the data to Bob, then they have a replica, they can work concurrently on this replica. And when they exchange those changes to each other, they again end up in a document where we have these 2 versions embedded. And you might say now, oh, there's still a conflict. But the difference now is that this conflict doesn't block them from continuing the work. For instance, Alice finds out that there is a conference called Elm Europe, and she just inserts the word Europe after Elm, and she doesn't care about rocks or rules. She keeps these conflicting versions there, and in the meantime, Bob hasn't heard of Elm Europe yet. He resolves those two versions. He decides again upon rocks, and then they exchange those changes, and finally end up with the same state. And that's what CRDTs guarantee. So CRDTs are called conflict-free replicated data types. It doesn't mean that there are no conflicts at all. It means that there are no conflicts on the data level and that you are not blocked in editing the data. The conflicts still remain on the application level. So on the application level, you have to offer some algorithms or UI to resolve a conflict. CRDTs have been around for a while in the academia and research for 10 years or more, but they're catching on in the industry now. And we are seeing several editors popping up. For instance, there is an Atom package called Teletype, which is running on a CRDT for collaborative code editing. There's the X-ray editor, which is work in progress by the Atom team, another standalone editor. The Sci editor, work in progress by Google, and RexPad. I'm really thankful to the guy who created RexPad because he borrowed me his laptop. He's here at the conference. It's Magnus Rex. He's sitting somewhere. You can reach out to him. He created RexPad and it's also built upon a CRDT. And we have several data stores and data bases. For instance, RIAC. Redis also has a CRDT data type, Cosmos DB by Microsoft, and BrightDB, which is my own humble project, which is still in its roots, but making progress slowly. Okay, now let's dive in. What are CRDTs in detail? And I found this nice definition on the internet. CRDTs are data types on which the same set of operations yields the same outcome regardless of order of execution and duplication of operations. So this might remind you of the definition of a pure function, because a pure function is also something where on the same input always yields the same output. CRDTs can be seen as a kind of a pure function with the additional restriction that the order of the input elements must not matter on the output or the duplication of these elements. So to put it more formally, CRDTs have to fulfill these three mathematical criteria: associativity, which means that grouping of operations and merging them should not matter, no matter how we group operations. Commutativity means that the order of operation must not matter on the outcome. And idempotence means that even if we have the same operations several times, it should always yield the same outcome. Well, for example, a counter. In a counter, we might need just one operation, the add operation. And the add operation takes a number, and our data structure to store of the CRDT is just a list of all the operations. Very simple. And as you see to the right, we have these add operations, and we can order them in any order. It will always result into 11. Or since each operation has a unique ID, 1, 2, 3, 4, 5, however this one is generated, we can duplicate operations and we can rule out duplicate operations easily. A unique ID might be a composition of the user ID and the timestamp or Lamport timestamp. There are various techniques, or it could just be a UUID. Yeah, the important thing here is that the result is always the same, irrespective of order, grouping, or duplication. Okay, now what about text? Text is a bit more complicated because text is a sequence of characters, and in an obvious approach, the positions, if you use relative positions to to construct our operations. So we have two operations, insert and remove. And if we have relative positions, then we have the problem that they are depend on each other. So we cannot reorder the operations in any way because it will result in a different outcome. Especially if we have concurrent edits, then we would have to transform one of the concurrent operations that it is transformed in a way that the character is inserted at the intended position with respect to the concurrent operation. This is called operational transformation, and this technique is used in Google Docs and Etherpad, for instance. But it has some problems. It's hard to implement. It's hard to prove its correctness. There might be cases where it gets the wrong result, I heard at least. And performance degrades rapidly with the number of concurrent operations. So, for instance, if the two peers are offline for a long time and they're making a lot of changes and then they finally are synchronizing again, then it's said that it takes a long time to make these operational transformations. So how would a CRDT for sequential data, for text, look like? And this is how ElmSEQ is implemented. It's based on ElmSEQ. There's a paper on it. And it starts with a layer. This is a layer. It's an array with 16 free slots. And when we want to insert a character, we first have to allocate its position. A position in ElmSEQ is called a path, for a reason you will see soon. And in the beginning, since there are no characters, we are allocating between the minimum possible path and the maximum possible path, which here is 0 and 16. And we are randomly choosing, pseudo-randomly choosing a position between 0 and 16. And in this case, it's 1. Because ElmSEQ doesn't just choose any of free slot in this range, it chooses from the beginning of the slot so that it is filled up more dense and not, yeah. You will understand it in the next slide. Okay, we get position 1, and we now can create the operation, the insert operation. The insert operation takes the user ID, the position, and the character. And we can store this insert operation in our history log, and we can apply this insert operation on our data type, and it will result in E being stored there. And the same for another character. We allocate it between 1 and the maximum path. It might be 3. We generate the insert operation, apply it on our data structure, store the insert operation in our history log, and here we are. And so on and so forth. So it randomly distributes those characters in this layer. And there are free spaces in between, because it might be the case that someone wants to insert characters somewhere in between. So for instance, Alice now wants to write Elm Europe rocks, so she starts with E, and she wants to insert the E between the white space and the R, so we allocate between 5 and 7. She generates the insert operation, and here we are. Next, we want to insert U, and there is no free slot. So what is happening? We create another sublayer, and in this sublayer, we can have all the characters which go between E and R. And the positions on the sublayer are then, that's why it's called a path. It's 6 for 6, the index of the first layer, and 4, the index of the second layer. And this position never changes. It is not relative to any of the other position. It is, you don't have to transform it. It will always be the same. It is unique. That's an important property of CRDT, that the operations are unique. Okay, and we need another operation, which is remove. It's easy. We just take this position 5 and store the remove operation in our history log. But we cannot just free the deleted slot. We can only mark it deleted, because we cannot have another insert operation inserting at the removed place, because then we would run into problems when operations are reordered So we mark it removed so that it can never be rewritten. Okay, that's how ElmSEQ works. Now let's look at an example in concurrent editing. So Alice and Bob start with an empty layer. Alice inserts ELM whitespace and sends those 4 operations, those 4 insert operations to Bob. Bob applies those 4 insert operations on his empty data structure and also gets the same result. He gets, now they're making concurrent inserts. And as you can see, the characters for rocks are allocated at the same positions as the characters for rules, because they're using the same pseudo-random generator seed. So it's always the same random numbers, but still random. And this way, we can figure out that those inserts are concurrent. But since those insert operations, those from Alice have the Alice user ID in it, and those insert operations by Bob have the Bob user ID in it, we can store those characters in a multi-value register and at the same slot having several versions of this in this place. This is how it looks like. And a different technique is the last write rinse register, which decides upon timestamps or something that one version always wins. But in ElmSEQ, it's a multi-value register, so that no data is lost, nothing is overwritten. And finally, since we have this history of operations, a third party can enter the game, and Bob can just send all those operations to the third party, and he or she will then have the same state as Alice and Bob. Okay. Demo time. Let me first demonstrate how it works, okay, before you enter the scene. So we're having here, I'm gonna refresh it to make sure that it's working. So we have 2 instances. On the left, come on. Okay. Let me just show it how it works. We have at the right, in the top right, we have the name of the instance, Rhodia, in the left, and on the right we have Carmela. And now we have here the peers which are available, obviously more than Rhodia and Carmela. And to emulate being offline and online, you can connect to Carmela, if I hit, now they are connected. It's a peer-to-peer connection through WebRTC. So hopefully it works out now in the massive collaborative way. So now they are working both on the same document, they're exchanging data. So Rhodia types Elm, Carmela sees those changes. Now, to demonstrate that I go, no, I don't have scroll bars. Oh, they have. Okay. So now they go offline again. And I forgot something. Sorry. Okay, I need a white space here. Okay, now they go offline. Come on. Okay. Thank you. Okay, just so they're still connected. No, that doesn't work. Okay, I mean, let's try it. It's okay. I actually want to demonstrate this multi-value register. Someone just made a concurrent edit, made an operations offline, then connected to someone, and it got synchronized to me. And we see those concurrent edits here. They are placed in a parallel manner here. And we can also, we do not need all those peers being meshed up fully. It's okay if we can make a if peer A is connected to peer B and B is connected to C, so C will get all the operations of A through B. So we can relay operations easily thanks to the CRDT. And yeah, it works great. And we can also show the deleted characters. Oh, it looks even more funny. Yeah, I mean, the user interface is perhaps not the best, as you can see. But it's a proof of concept that we can massively replicate stuff. And it is quite fast. And it's always the same result. Okay, I have another slide.
How to deal with conflicts, though?
Yeah, you resolve them by just deleting what you think is too much. For instance, here in this place, there were 4 concurrent operations happening. Okay, 4 concurrent edits, and someone already deleted those 3. So if I don't show the deleted characters, you only see the P. So this way the conflict is resolved. But the deleted characters are still there, but you don't have them on the screen. So it is on the application layer that the conflicts are resolved. Okay. Okay. Should we keep this running, or should we type questions here? Okay, I have another slide. Then it's actually... Or do we have time for the code? Do you want to see Elm code, or do you want to check it out yourself? Okay, I'm just going to show it shortly, how it is implemented. It's in brightdb/sequence, and it's quite easy. We have those layers. A layer is not an array, it is an int-dict, because I think it takes less space. And we can access elements before and after an element in the int-dict API, which is useful for getting the for cursor moving, for instance. And there's the layer items, and the layer item is either an item or a sublayer. So in a sublayer, as you've seen, we store all the characters between 2 other characters. And the item can either be, an entry can be single or concurrent. So in the concurrent form, we have the MVR. This is a multi-value register. And the multi-value register is just a dictionary of mapping user IDs to a value. And the value is either a value or a tombstone. And the tombstone, a tomb value either is a tomb value we know or an unknown value. We need the unknown value in the case that we get a remove operation before we get the insert operation. So we can insert a tombstone of an unknown thing, and later there might come the insert, and the CRDT turns this unknown tombstone into a known tombstone, a tomb value A. And we have the operations here, which takes the path, the insert and remove operation. Yeah, the insert and remove operation is here. Yeah. Okay. I don't know. Where is it? How do I get? Ah, yeah, here it is. Okay, the last slide. You might know the reactive manifesto. Reactive systems need to fulfill these principles. Need to be responsive, so be performant. Resilient means don't bother with errors or conflicts or whatever. Message-driven, so yeah, we have that in Elm all built in. And elastic means we can easily replicate stuff. We can scale the system, and that's what CRDTs all fulfills. CRDTs are a perfect match for reactive systems. So here are the links of the package and the source code, and I actually had the slide, didn't upload it, but you can also find the slides at brightdb.com/ElmEurope18. Thank you.
Thank you very much, Matthias.